Let us start with introducing ourselves. I am Tomasz Kowal and this is Janusz. We are both students at AGH University of Science and Technology, and we are here to talk about Erlang-based software update platform for remote devices, which was our bachelor's project this year. And let's start. Here we have some content. Firstly, I will describe the device we are talking about. It is Beagleboard, so Michał said something about it earlier, so I will keep it short. Then I will describe an example why do we need such a platform. Then some requirements and why did we use Erlang to do it. Then Romek will deep into the architecture. Okay, so this is Beagleboard. It runs 1 GHz processor. It has 512 megabytes of RAM. It also has some USB ports, HDMI, so we can connect keyboards and monitor to it and use it as a desktop computer. But what is most important, in our case, it runs Linux Debian, which is installed on the SD card. Okay, now let's imagine we want to have a network sensor network. So, like in Michał's presentation, we want to measure, for example, traffic in Kraków to plan building new roads. And what do? We buy 10,000 of Beagleboards, we attach some sensors to them, then we build our software and test it carefully, of course. Then we have to place them in key points in Kraków or even in our cars. And those devices can connect via a GSM network, which is rather slow. It has low bandwidth and it isn't reliable. We can imagine a device in a car which is passing through a tunnel and then it loses coverage. So now we start collecting some data and then bang! We found a new feature in our code which we want to fix really fast. And now we have a couple of options. We can change SD cards in our devices, but let's be serious, we have internet access, we can do it remotely, right? Right, but not exactly, because firstly, those devices can be behind NAT, so it would be rather difficult to use, for example, secure shell. And secondly, there is 10,000 of them. So even if we write some script, we can have a situation where some devices aren't connected to internet at this point in time. That is why we developed our platform, and we wanted it to perform mass automatic updates. We just specify which software we want to update, on which group of devices, and then it runs automatically. If we wanted it to be reliable, because we're using unreliable network, and we want to get the job done and recover from occurring errors, we want fine-grained control over upgrade process, not only stop the system, upgrade, and start it again. This is too easy. We wanted it to be easy to install and use, and also we want to send as small amount of data over the network as possible. That's why we wanted to use Erlang. It is massively parallel, so it can manage thousands of processes, which makes handling a large amount of requests from devices quite easy. It is fault tolerant, using supervisors described by Michał and other OTP design principles. Makes it easy to recover from errors. And it gives us hot code swapping, so we can update software on our devices without stopping it and without losing its state. We also integrated it with Package Manager because it's very easy to use. Every software administrator used DPKG or some other package manager before. And it also help us save some bandwidth, which we'll talk in detail in a moment. Now, I want to be sure that all of you know these terms, like what is OTP application or Erlang release. Is there some people who don't know these terms? Or who knows it? Okay, I think we can skip this part, because it's really key to understand the rest of the presentation, but most of you know all of these terms. Okay, so now I will pass the microphone to Romek.
Okay, so I will get more into some design and implementation details of our platform. And here's a summary of what I'm going to talk about. First, I'm going to talk about the remote software development model, because we have assumed some concrete model of how the developer of our Erlang application installed on a device like this is done. So I will talk about it a little more later. And then I'm going to talk about package manager integration that we have incorporated into our platform. This is a very important part of our platform. And these 2 points actually relate to the device. And then the next 2 points consider the platform as a whole and get into more details about the server. So, okay, let's start it. So firstly, the development model. We have a few important assumptions here about how the developer writes the application and the software installed on the Beagleboard. So first of all, the application, the software that is installed on the Beagleboard is a single Erlang release in an Erlang distributed node. So we must assume that the developer maintains an Erlang OTP release. The next thing is that the main tool for building and compiling this Erlang release is Rebab. This is quite a standard tool right now for building Erlang applications. You can compare it to, for example, Maven for Java or something like this. The purpose is pretty much the same. Compilation, build of the release, build of packages, and so on. And these are all standard Erlang ways of developing the node, developing the release. We added some our own scripts into it because we wanted to make it a little more integrated into the platform. So first, there's a general script with which is used to generate so-called relap scripts. The relap is a script that defines the way a release is upgraded from one version to another, or downgraded. And Rebab can do that, but we need some more fine-grained control over it, so we need our own script for this. And finally, we have 3 additional scripts which are used to generate Debian packages for our node. Because, of course, this would be very, very tedious if we do this manually. Okay, so this is about the development model. And I mentioned that the integration with Packer Manager, so I will talk about it in detail right now. Okay, so what do we mean by integration with Linux Package Manager? Linux Package Manager in our platform forms a layer over standard Erlang mechanisms used for software installation and upgrade. And like this, so it is done in a way that Debian package maintainer scripts invoke standard Erlang mechanisms that have all those cool features like hot swapping and stuff. So, as I said, we preserve ability to gain from hotcode swapping, and thanks to that we have very fine control, very fine-grained control over the upgrade process, because of course the developer can define in much detail how each application is upgraded from one version to another. And Another benefits, general benefits from use of package manager as follows. First of all, this is it allows us for very easy maintenance of remote device and the node installed on it, because the installation is just running get install. We don't even need to install Erlang on our device, because the Erlang node is self-contained. It contains an Erlang runtime and everything it needs to run. And one more important thing for package manager integration is one more benefit is that thanks to automatic dependency resolution provided by package manager, during upgrades less data is downloaded, and thus we save bandwidth of our very slow connection GSM as we told earlier. Okay. I may mention also that Reber is able to generate an upgrade package, but the way it does it always includes all the applications of the release into the package. So even if only one application changed in our new version of the release, we need to download every application in the package. So that's why. That's where the package manager really comes to help. Okay. So I will now get into some more details about how the Erlang node is decomposed into several Debian packages. We implemented integration with Debian packages, but we had in thought that this may be any package manager for Linux, like Yum or Pacman. So this is something for future development. Okay, and the details about decomposition into the packages. So our Erlang node is decomposed into several packages. The first one is the main package. This main package on the top represents Erlang release. And this one is very important, although it does not contain any code, actually, because it contains only some configuration files and the definition of the release itself. So this is the only package that system administrator should directly operate on, because our assumption is that the Erlang node always must be installed and upgraded as a whole. And the only reason for decomposition into several packages is that automatic dependency resolution that package manager gives us, and thanks to that we have less downloads. Okay, so this was the main package. This main package is dependent strictly, that means by a concrete version, on application packages. We have one package for each Erlang application, and there are three groups of these packages. The first group contains standard Erlang applications included in pretty much every release, like kernel, std lib, like inets, like SASL, and these are likely to not be changed. Okay. The second application package is the software update platform client package. Contains software update platform client application. This, of course, the application that is responsible for contacting the server, and of course, it is needed for our platform to work. And finally, we have a set of packages that are user-defined and contain the actual code that the user of the platform writes. And finally, all those packages are dependent on the base package, which contains Erlang runtime and so basic scripts for running the node that are generated by Reber. Okay, so if my display allows it, I may show it live. So right now, all the packages that I explained later, before, excuse me, are being installed with base package, all the application packages, and the main package. Also, for this, we have some trouble right here. So, regardless, I'm going to go back to the presentation. So, right now I will talk a little more about the architecture of our platform as a whole. So, this is of course server-client architecture. On the left side we have a remote device, and this is of course this one. There's an Erlang node, all the applications that I explained, software update platform client, everything running on Linux, and DPKG helping the installation process. So, and on the right side there's a more interesting thing. There's a server. The first component of the server is the HTTP server. It serves two purposes. The first one is the web UI, and the second one is the different package repository. The next component is the management server. This one, of course, is for management of the devices and scheduling upgrades and doing configuration. And final component is the database, which right now is in Asia. This wasn't much of a focus for us. If there is some need for scalability, it can be changed, for example, for with CouchDB. And the database also serves as some kind of communication channel between those two servers, HTTP server and management server, because they, in current architecture, do not communicate directly. Okay, so I will now talk more about the middle part, that is the communication protocol. Okay, so communication between devices and the server happens in a sessions manner, so-called management sessions. And it is our assumption that the session is always initiated by the client, by the device, because of course it can be behind an NAT or something like this, so we cannot assume that we can initiate a communication from the server. But we of course assume that there may be some way to trigger the device to force it to start such a session, and that's why we consider the possibility of connection request. But of course, how that connection request happens depends on what our network allows. Okay? So, about the protocol itself. It is very simple because it is just over TCP, and we can send pretty much everything that we can define in Erlang, any Erlang term. It is serialized with term to binary and binary to term, and it can be sent very easily to TCP, GenTCP. And it is, because it is generic, simple, and extensible, we can think of expanding our platform into a more general management platform with only for upgrades. Okay? So, these are some details about management session. I may not get into it. Okay, I will try to perform upgrade. I'm very sorry that it may not work because of some very silly mistakes that we've done probably. I will just now show the UI of the platform. We have the device here. It registered itself to the server when we started the node on the device. We see some bunch of information about it here, all versions of applications, and the release itself. We also have some UI for repository, the package repository. Okay. I can see that now I know why my presentation went wrong, because I forgot to delete the new versions of our packages. Very sorry for these mistakes. Right now I should be able to perform it in how it should be done. So okay, let me do just one more thing, unless we don't have time, right?
We do have, no worries.
Okay. Okay, so just to make it a little... Okay. I just delete only the packages that are most important. Okay, so the node was stopped automatically by maintaining scripts. Write down the right versions of the packages and installation. And now it should be a little faster. Okay, so that's the first version of the sound. And right now I'm going to perform upgrades to change the sound to this one that we heard earlier. So this is very easy done from the UI. Okay, get into the device. First, oh, okay, I forgot to put it in the repository. Right now we schedule the upgrade. We can see some progress about it. It may take some time because the device periodically contacts the server. Right now it's probably 10 seconds. But this is of course configurable. One or more time and everything should be fine. Okay, this finally. And we have the changes reflected in the UI. We have the version 2 and the version 2 of the application. So sorry for technical problems. We'll be now getting back to the presentation. We have just some summary here. So what did we actually do to summarize it? So first we have some concrete level of development of the application on the node. As we said, with the use of the driver. We have mass management of devices and scheduling mass upgrades. We can schedule an upgrade on a group of devices. We have a UI for that. So we have easy maintenance of the device thanks to package manager. And we also, of course, benefit from use of hotcode swapping. We also optimized the size of downloads during upgrade thanks to the usage of package manager and its automatic dense resolution features. And of course, we do have hotcode swapping and fine-grained control over upgrades. So, just a little words about future development. So as I said, it can be expanded into more general management platform because of the very extensible protocol, very simple one. Of course, the obvious way we can extend our platform is to integrate more package managers into it. And finally, the final thought, maybe a little more difficult, was to implement support for distributed Erlang applications running on the cluster using native Erlang UI, native Erlang API for connecting into a cluster. And here's the repository with our code. It's open to commons, so thank you very much. maybe any questions?
Have you considered, as far as now, DPKG has some support for downloading only differences between packages? Have you tried it to optimize the size of downloads in Total?
You mean the feature that not only downloads the packages that have changed, but even going more deep into it, right?
Yeah, there is some experimental support.
Okay, this is a very good thought. We may think about it. Thank you for this advice.
There is I don't know how to call it, a piece of library. It's called Framework, and it's dealing with using Debian Package Manager to upgrade Erlang applications altogether with release handling or release updates. Did you heard about this, or did you found this, or you did not found this?
Okay, we were looking for such software which would help us integrate DPKG and native Erlang mechanisms. We didn't find this one. We found one that was able to do upgrades on separate applications independently, but we need something more. We needed to update on the whole release, and DPKG actually it was a little hard to do with DPKG because the most difficult thing was to find a moment in the upgrade process by DPKG in which we have all the old versions of applications and all the new versions of applications present still, both on the file system. I don't know if this framework supports this.
You have to look closer.
Okay, so thanks for your advice.
Together with package managers, package manager use hot code swapping, yeah?
Yes.
So it's possible to reinstall the software without rebooting the application?
Yes, that's exactly what happens right now.
So it's possible to use it together, a package manager and this hot code.
Yes, exactly, because Debian packages contain maintainer scripts, which are invoked in different phases of the upgrade to download package manager, and we created templates for those scripts. And those scripts invoke actual operations on the node running. So they invoke so-called release handler of Erlang. And thanks to that, we are able to benefit from hot code swapping.
You do some tests with a large amount of clients to see how it scales?
We didn't do tests, but we may suspect the initial requirement of how many devices we should handle was about 10,000. And I think this is not much, actually. But of course, we hope that Erlang solved this problem, and that's why we chose it, because we have all those lightweight processes. They can run concurrently, and there can be a very large number of them. Not like, for example, in Java, where we can have only some certain amount of threads, and then it stops scaling. And right now, the implementation right now is that every session is handled in such one lightweight process. So we think that we hope that this shouldn't be much of a problem.
How long-lived are those sessions? Are they very short, or does it stay connected all the time? I mean, is it polling or pushing?
Session starts with an inform message from the device, and then the server processes this inform message from the device, logs some data from the database, and then decides what to do. It sends some job to the device, then the device does this job, sends the result back, then the server decides what to do then, what to do next. It may be some other job, but also maybe termination of the session. So this is pretty much simple, like inform, request response, and
you mentioned there's interval of connections is 10 seconds, so 10 seconds and 10,000 nodes. It won't. I mean, the problem with polling is always either you have too long intervals, or your server is non-stop overloaded because there are very large amount of connections happening all the time.
Well, of course, the time, the interval of that defines how often does the device contacts the server is of course configurable. Right now, this example value 10 seconds is way too small, as we think. And it is configurable, so it can be configurable by the server itself. We may consider adding it twice, so we may implement some kind of algorithm which will, for example, if we see that the device contacts the server too frequently, we may change the value, and it should be better. And still, we have the possibility of connection requests. So this interval can be long when we have the possibility of connection requests, but because then we can trigger the device to contact the server from the server side.
I would like to also add one more thing. When we trigger update, the session, the TCP session lying under our session is very short. We just, the device pulls, is there something for me? And then the TCP connection, on the TCP connection is, yes, it is. And then we run DPKG, so DPKG runs all the rest. So TCP sessions are very, very short.
Thank you very much.
Thank you very much.